All right, so thank you for being here. Today we'll talk about medical device security and the learnings we got from countless security assessments. My name is Julian. I'm Senior Security Analyst at ENW, and I have a medical device background and also studied medical computer science. So know the environment in the end. My commilitons are working in hospitals or building those devices for themselves, so also got some experiences from them. And I performed more than 25 medical device security assessments. I think not at the moment it's just going to the 50s. And today I want to share the experiences we got from those assessments, the pitfalls we saw that manufacturers have when building those devices, and maybe also we will talk about the regulation that was introduced in 2017, the medical device regulation, and the changes that may be there that change the way that the devices will be manufactured and how they will be operated in the end, and how these changes may impair or make it better in the end. So the agenda is that we will have the case studies first, then we will go to the lessons learned from those case studies. We'll talk about regulatory requirements, and then again talk about disclosure processes and the experience we had from those. And we'll then get a short summary about that. So we will start with the case studies. The first example we will talk about is a patient monitoring system we assessed in the course of a BSI project, so a project from the Federal Office for Information Security. We performed some assessments for them in 2019 till 2020. The project was named MoneyMed, Manipulation of Medical Devices. I think few of you may already know that. And that was one assessment in that course. And when we're talking about patient monitoring systems, we first have to have a look at how the infrastructure is being put together. So we have a central monitoring service where all the measured health data is being transferred to, where the devices are authenticated, where the users are logging in. So that's our central point. And we will have different patient monitors that are connected to the patients, measuring their health data, their vital signs, and we'll connect it to or communicated to the central monitoring service, where also surveillance stations are being connected to. So you can review that health data from every point in the hospital just with such a surveillance station, and also you can review the data of patients from other patient monitors. So it's a highly connected system using the normal hospital network. And further, we have network-connected systems such as patient records or data archiving systems that are also clinical, but not in the power of the manufacturer of that system in the end. So we are communicating with external systems, that means such for documentation, for example. In those systems, we of course need a common trust anchor, and in those means, in that environment, that was an environment certificate authority with enrollment functionality. So every device and every service in that environment got a certificate in the end to perform mutual authentication via UDP. So there was a proprietary communication protocol that the manufacturer implemented on top of that security channel where the devices talk to each other. And as already said, the devices also were able to communicate to other devices, not only to the central monitoring stations, so we have to build that up with that trust anchor too. The problems we found were basically that we crashed everything in there. So first we found a vulnerability that enabled us to crash the central monitoring service. So the devices were not able to just deliver the health data anymore. So you had to go to the device in order to review it. Then we also saw that that certificate enrollment service was vulnerable in the means of the certificate signing request you provided. So you could crash it by basically parsing that. And also that service, when being enabled, was not protected by the means that you are not in the position of simply getting such a trusted certificate. But that was not the largest problem, because the biggest issue was that there was no means to revoke those certificates. So when you got in the position of one of those certificates, you basically could talk to every other entity in that environment, and that enabled us in those means to talk to those devices and to fuzz that communication protocol, which in the end led to some crash of that device. So we were able to impair the complete medical device network by simply talking to all of those devices and crashing them. And that basically has shown that the interrupted monitoring and access to patient data was possible via that interfaces, but that the trust management in that environment was the biggest issue besides of that implementation bug, because there was the assumption that only trusted entities can basically talk to those devices. And we basically broke that assumption in the end. The implications, of course, also were that when you're designing such systems, you have also to consider the disaster recovery. So you have to assume that there is a compromised entity in your environment. You have to handle that entity, and you have to think about means to reduce or to terminate the trust in that device in order to have or to maintain the trust within the environment again. And this was the biggest issue in that case. Further, of course, you can design nice processes and nice functionality. The operators need to have a description about those processes he has to implement. So how can he determine that the device is compromised? What does he need to do to revoke those certificates? And that means, is that enough? How can he review which device basically has sent health data on which then medical decisions are based on? So how can he, in his processes and in his dedicated and specific environment, use those functionalities in the end? So you have to think about rendering that operation feasible in the end. So not that security is basically in the environment, but you can not use those functionality because nobody knows about that. And then it's basically impairing the operation of such an environment. Another example I want to talk about are infusion systems. We also had different advisories about those. Normally they are put up like that you have your medical devices, the syringe pumps, that either are directly communicating with some central monitoring and infusion system, or you have devices that don't have communication interfaces, but are stacked together in such docking stations which then for themselves have that communication interfaces, so they act as a gateway for those devices. And also, again here, the central infusion data management system then is the gateway to other clinical systems that are not belonging to that environment. And so that's how that environment looked like. And there was no remote control functionality, so that's also important to see. You could not control those syringe pump. It's solely for documenting the drugs you're delivering to your patients. So pretty not that spectacular in that means. But when you see the findings, we basically, again, compromised everything except for the medical devices. So we found multiple vulnerabilities to, in the end, bypass the authentication mechanism being authenticated in that docking station administration web interface. We then completely compromised that, also got root access in the end. And also the central management service was that insecure, and it means that there was an unauthenticated upload and download functionality for settings. And having that with the path traversal, we then hijacked basically a third-party library that just included to get code execution in the end too. So what's the impact? There is no impact for the medical device, but everything else is broken. So how do you handle that? Because there's no patient safety impact. But I think it's still not good to let it be like that and to not act about that. But having compromised the docs, you are able to communicate with the medical device. So basically that's the prerequisite for more attacks. So that's where you normally want to start your assessment of the medical device. So you have also to consider security vulnerabilities in medical environments where no direct patient safety impact is present. And also you can see that maybe the effort the manufacturer had was put in the medical device, but not in its accessory in the end. So you have to consider everything you're building and not only the certified stuff. Then we're going to the third case study I want to present. That was a vital signs monitor. So similar like the patient monitoring system we saw, but only one dedicated device, which is used in smaller environments or where you have to have that a little bit more mobile to move it within the building. That monitor had one interface. You connect that to your communication server, and it was what's the beamer? Okay, Yeah, and this device was basically talking to also some documentation system using that medical standard health level 7 version 2. And that's a text-based interoperability standard that was introduced in the 1980s. And yeah, was basically built to enable interoperability of a set of different systems. So it's not only used for medical communication of diagnosis and observations and their results or something like that, but also for the billing, for the admissions and such interfaces like that. So all basically medical systems from the past were using that standard. What we found was kind of funny also, because that patient monitor had a barcode reader connected, so you could scan the patient barcodes to not have to enter the patient data, patient record ID and something like that into that. And what we found was that the user interface did not allow to include special characters into those input fields, but you could basically scan that with the barcode. So we introduced our payload using the barcode reader, and we were sitting there printing out our payloads and scanning that with the barcode reader, which is also not that usual for security assessments. But yeah, in the end, we could inject new segments into those messages, and that enabled us to introduce diagnosis codes into the messages that the device was sending to those connected services. And you can see that it's basically Wireshark, a screenshot that the payload we added on the previous slide with the new lines was introduced also into the message the device sent into the network, and also that the message was parsed and processed by the connected system and was acknowledged, so that was considered valid in the end. And also you can see that even the Wireshark dissector added and parsed the diagnosis we added with the medical coding system ICD-10. And what's the impact from that? Because we didn't attack or compromise the device in the end, but obviously some connected system there's a trust relationship between that device and some network connected system, but we don't know it really, but we are exploiting it. So I think it's a nice example where you can see that you also have to consider which device or which system in such environments is communicating with each other, and that you may not trust the device for itself, but also you have to trust the data it's sending to you. You have to validate that, because there is no medical use case where a patient monitor is adding a diagnosis into a patient record. That's not how the device is being used. It's not even capable to insert such information. So the next case studies I want to talk about are insulin therapy systems and point-of-care testing devices. We will start with the insulin therapy systems. That's the largest set of an insulin system you could have, because insulin pumps normally do not measure the insulin level or glucose level of a patient, but that's what a glucose sensor is doing. And the insulin pump normally is just giving the boluses with the rates you defined, and then it's basically fine with that. And in that loop system that we have drawn here, there's a mobile app that is reading the values from the sensor, and then it's deciding whether the patient needs some insulin bolus, and then it's administering it by communicating to the insulin pump and telling it, please administer that amount of insulin now. And then the pump basically is doing that, and that's completely in the hands of the mobile app. So the patient one time has to configure that app and that logic, and then it will be just replacing the insulin in the pump somewhere. And such a system, of course, is interesting with that right functionality to the medical device, because when you hijack that, you can administer insulin. So the impact is clear. What we found in that assessment is that the communication protocol was completely broken. It was a self-built protocol, and it was on top of Bluetooth. And as we can see on the slide, there are different colors, and those different colors resemble different encryption that they used. The yellow one is some encryption they were using with the device serial number, so basically that broadcasted itself with that, and then you were able to read that communication. And after that, there was some further keys being generated, the blue one, where then a pairing key is being transmitted. And if you got that pairing key, that was the simplest or the solely used authentication means that that device had. So if you got that, then you were basically the trusted mobile app and could administer insulin. There were also further vulnerabilities like hard-coded credentials, missing replay protection, client-side authentication, insufficient random values, so you could just choose something from the list of vulnerabilities you could have in custom-built protocols. But the impact was, the biggest you could have with that, because we built an exploit for that, hijacked that pump, the existing connection between the pump and the mobile app, hijacked that, terminated that, for us, communicated with the pump, and then just emptied the insulin of the pumps. And for the demo, I replaced that with blue ink, but I think the impact is completely clear. You could also try to terminate that, but the exploit is that smart. It's not administering one large bolus, but multiple smaller. So you have to continue doing that, which will not succeed. So the only means to terminate that attack is by removing the insulin pump from your body. So what's the implications and the mitigations from that? It's basically that you should not roll your own cryptography, and that you should use the security functionalities from the protocols you were using. So they just used Bluetooth as transmission feature, but not use the pairing or bonding features that Bluetooth is offering. So they just implemented everything on the application layer, and that failed, obviously. And then, during the disclosure, we had the problem that the device was not designed with residual hardware resources that enabled them to use those security functionalities of the Bluetooth chip in the end. So they, again, fixed that by fixing the app layer protocol, not by using the standard features that the app transmission layer protocols were offering. And also, that's something you can see on the point-of-care testing devices. So the medical purpose of those is that you're going to the patient bed and taking a little bit of blood from the patient, and then, for example, measuring the glucose level or other values that are easily detectable with those testing kits. And also, some patients may use that at their home use or something. So it's smaller devices. They normally have very limited interfaces, and are not wired, just portable and used for those testing stripes. Technically, those are, of course, embedded systems. You have very limited resources with smaller microcontrollers and SOCs or similar. You have embedded software stacks, real-time OSs, and few software abstraction layers. So normally, they're just doing UI code and memory management in the same code, which could have impacts, of course. So the communication interfaces were USB and also serial interfaces, so that's where things are getting pretty interesting when you have colleagues that never saw a serial interface because they're way too young for that. But that's still things you see in devices that are developed in the 2020s. And also, of course, Bluetooth and Wi-Fi interfaces. The vulnerabilities and challenges for that are, of course, the product lifecycle issues. So you manufacture such a thing, you market that for 15 years with limited resources. You have an outdated OS after just marketing that. You have the problems about the firmware updates. So most of those devices had broken firmware updates, and I'm talking about tens of assessments of such devices. And also, you have vulnerable third-party systems or libraries and dependencies. So the manufacturer may fix the bugs he was finding in his source code, but often forgot to also upgrade the libraries he was using to build that in the end. And then, of course, the design and development problem. So we saw hard-coded secrets in basically every means you could imagine that, also hiding that as images with just changing the extension. And so there were many things that you don't want to see in a medical device in the end, and also just implementing AES for yourself or Bluetooth stacks because the library you wanted to use is too large for the flash you got, or implementing TLS and OpenSSL for yourself, for example, and building your own encryption authentication protocols like we saw in the insulin pump. So that's daily business you may see with such embedded devices. And also, there were some operation issues like unprotected service interfaces that were just there for debugging it when the device was not operating normally. And also that you may have seen that the device was updated in the past and got a secure version of the protocol, but for compatibility issues, it just enabled that additionally and did not remove the insecure one. So you again could attack it on the insecure one, but well, okay. don't know what they thought about that, but the compatibility thing is, of course, for larger environments, a big issue you have to handle in the end. The lessons learned from that are that most vulnerabilities we saw about it are basically not medical by themselves. They are just the normal IoT vulnerabilities you may see, but obviously the operational environment and also the impacts you may see are the thing that make the medical devices special to that. And also, the lessons learned, of course, are that the devices should have designated resources for being updated in the future, that they should not just implement it and ship it like, get it on the market, but of course think about future updates and residual resources that you need for upgrading those devices and also upgrading the security features of the device. Yeah, so let's come to the regulatory requirements I already announced. The medical device regulation was introduced in 2017 with some sister regulation, the EVDR, and we will mainly talk about the MDR in that context here. The regulation is in force since 2017, but there was a transition phase until 2020, but with Corona that was delayed for 2021. And so that's the regulation that is in force and has to be applied on medical devices now in the European Union. The relevant changes for us in that context is the safety approach, and that is basically now based on the entire product life cycle, and also that is requiring hard quality and risk management on the manufacturer's side, and also intense post-market surveillance activities, which we will see later on. As regulations are normally not that specific about real demandments that someone has to do about his medical devices, the European Union basically put on the Medical Device Coordination Group, which is a committee that's only purpose is here to explain and interpret that regulation in the end by releasing guidances on special topics. And we will cover the guidance on cybersecurity for medical devices by that MDCG. That MDCG also is really nice in the means that when you read it, you will read it as a security researcher as someone just noted your wish list, because it's really nice from that point of view. We will just see that later on. And also the MDR is telling that any risk associated with the operation of the medical device must be acceptable, and that actively includes security risks. And MDCG makes that a little bit more clear about the balance between the benefit and the risk. So the manufacturer has to consider everything that could result in a risk, and also the relationship between safety and security. That means if you're having or designing a security measure, then that must not have an impact on the safety of the device, but also a security issue that may impair the safety or a safety mechanism must also be considered. So you have to have a balance in here and to have to handle that relationship between those two in the end. The requirements from the MDR basically are that the manufacturer must implement state-of-the-art security capabilities in his device, and that's where the regulation does not tell you which requirements that are, or which capabilities those are, because that's what the manufacturer in the end has to decide on. And also it's demanding that there are intense security verification and validation testing processes, and you have to document that. And as with the previous law, you have notified bodies that will audit that when you want to market your device. And the best way to document that, from the MDCG perspective is to show that you're doing assessments. And the MDCG is also telling that you have to do fuzz testing, code scans, pen tests, and different stuff. So things you never read in any of the other guidances before. So it's actively demanding to do so by the manufacturers. And also that this effort is not something that you're just doing once for your documentation, but that you have to also make clear that that is not a one-time show you're doing, but that has to be included in all the other testing activities you're doing as a manufacturer. So that really needs to be in the DNA of that device in the end, and in your processes that you're doing verification testing by the means of security testing. And also the MDCG is telling the manufacturers, I think, no-brainers about the life cycle aspects, because it's telling you that a device can only be considered secure at a dedicated moment in time, and if you don't do anything and don't add further security functionality, or that you're patching your bugs, that you're not assessing that, then it's just secure for that moment, and it may be vulnerable in 5 minutes after that. And that's basically the motivation for those continuous efforts he has to put on the post-market surveillance. So he has to do assessments after the device is on the market. He has to actively and regularly monitor such risks, and he has to implement actions actually, and to roll out those actions to the field in a short time frame after he performed a risk assessment, of course. And the most interesting thing also is that he has to actively collect that experience from the market. So when there is a hospital, for example, that's also performing assessments on that, then he has to consider that feedback. And also that thing is opening the door for something like bug bounties, or more like disclosure processes. We will come to that also later. I think it's also interesting to see that the MDCG is just noting also the third-party software and hardware in here, just not that the manufacturers are forgetting about that point, that it's not only about their own code, but also all of the code they're using. And also, the regulation is telling them that they have to timely implement those measures and corrective actions. So that's what the PMS should include, but then it's also specified that that's being audited by the notified body, but also that a successful and well-audited system should, of course, include sharing and disseminating the cybersecurity information and knowledge about vulnerabilities, which means that the regulation basically is demanding manufacturers to do security advisories. And I think that's a huge improvement from the last regulation, where the manufacturers were silently patching and rolling out the fixes with feature updates or similar, and did not actively communicate that there were potential safety, or not safety, but security risks with those devices, because with the safety issues they had to act, and they communicated at least to the operators in the end, but not to have that transparent for everyone. And also, that they of course should include updates to all the different layers of software they were using, their own builds, like updating the medical device software and updates, but also providing the operators with short-term measures like mitigations they should do, like isolating the device or similar, when building the update, to also tackle the risks in a short time frame when it's not possible to fix the vulnerabilities that they identified within a reasonable time frame. So I think that's also a huge improvement to the last regulation. And also, there's the problem, again, with the software updates and the recertification. So normally, when a medical device is being changed, you may in the position of reporting that to the notified body, which then will come to you, audit all your processes, documentation, and then you're allowed to market that, actually. That's where another MDCG guideline, the 2020-03, clarifies that you can change your device and also patch that without needing to do that in the end when it's a minor change. So when you're not controlling an existing risk with your changes, then it's completely okay to do so without notifying your notified body. But when you're actively reducing security risks that have safety impact, then it's a major change. You have to document it, you have to report that, and also you have to communicate that transparently. So it's a huge improvement. We may also talk about the supply chain in those means, because I think a few of you also know the software bill of materials that was discussed in the past. From my opinion, it's completely useless for the operators, because just having a list of the used software in that device does not help you when vulnerabilities and those third-party components are getting public, because you're not in the position to assess whether the vulnerable code is even used. You cannot assess the risk with that. You don't know if the device really is vulnerable in the end. So I think we have to discuss about which audience that SBOM basically is needing, and what the real audience, so the operators, are in the end needing for themselves to be able to act with their business. So That's where some other standard is getting interesting, the Common Security Advisory Framework, which is a standard for security advisories that's being developed at the moment in the second version, and that is being mapped to the SBOM data you have. So the SBOM is not completely useless, but it's the starting point for mapping security advisories on that, so you can automate that in the end. And also that the manufacturer that's using third-party components does not have to collect different advisory formats to pass them, to process them, which is a lot of work, of course. And that CSAF also has some nice profile, which is the vulnerability exploitability exchange profile. And that is basically used to communicate also with advisories whether your product is vulnerable and what you could do to fix that or to mitigate risks you are seeing. So that's basically opening the door for releasing multiple advisories with fixing states or similar about the vulnerabilities in that, and you're not telling, there are vulnerabilities and they are now fixed, but you can do that way faster. And I think that's the relevant information for also the operators in the end, that when you're getting such a digital document completely automatic, that you know which devices you have in which software versions, that you can map that, and that you have the things you need to do to control the risk in the end. So it's basically written in there what you need to do to operate that device safely in the end. And I think that's the information you need, and not that there's some vulnerability in the component you're using. Because you're not in the position to controlling that in the end. Yeah, because also in most cases, the vulnerability in a downstream component will not be exploitable in the upstream software. So there's a lot of noise in that topic, in my opinion. That is not that necessary when we think about what information we really need to communicate to the operators. So that's the point where we also go to the vulnerability disclosure processes and the experience we got from that, also with the project money made with the Federal Office for Information Security. Because normally you will not do such processes in customer projects, obviously. But so what does the MDR tell about vulnerability processes? Because we already heard that sharing and dissemination of cybersecurity information and knowledge about such vulnerabilities and threats is important and considered a best practice and a requirement by the guidance. So I think it's basically opening the door to security researchers that the manufacturer has to act in the end, because in the past that was somehow different. Normally, there were few manufacturers that published a real vulnerability disclosure statement or contact information, so it was really hard to contact them when you found vulnerabilities in some research in such a device. Then with that safety impact thing, you normally had to prove for yourself that there is a safety issue in such a medical device, because otherwise the manufacturers may not have acted at all, or has delayed the process, for example, because of prioritization issues. And also, the experience we have is the complexity of such disclosure processes. So when there's the device and you have to fix that vulnerability, you always have to consider that there needs to be a time frame where such updates can be applied in the end. So normally the operators then are basically getting DOSed by all the software updates they have to install on their devices, and that's something you don't want to have when you're not fixing all of the vulnerabilities in one batch. So you're not getting out of the process of updating your devices in the end. So that's one thing, but also it's the different thing that you have to consider the development processes and the release cycles of the product in the end. So the disclosure normally is not a starting point for rolling out a software update, but that may be some other trigger that's already in the process. And also, what's delaying the processes normally is that when you find a vulnerability that is simple to fix, then it's easy, but mostly it's not that easy, because when you spot a design flaw or similar, then you just simply cannot change the line of code and roll that out to the field. But you have to consider the devices where you know that they are basically broken, that they have not residual resources to really fix the vulnerabilities. How do you proceed with such disclosure processes in the end? So it's a big issue about that. And also, there are also often contracts where the device is not being patched by the operator himself, but by the manufacturer and some service technician that is coming. And if you imagine that we have 650 hospitals in Germany, and each of those hospitals is using, for example, 2,000 syringe pumps, then that will take some time when you're installing an update with 10 minutes on each device. So that's simply a practical issue you have to handle in the end. Yeah, and also, the communication issues you may see. So the processes were really stagnant at that point, and also you had ambiguous statements about future actions, because when you did not prove that there's a safety impact, you did not really see what the manufacturer was doing afterwards. And also there were some manufacturers that simply told you, yeah, we got the report from you of the vulnerabilities, that's really nice, but we're not allowed to share any information about what we're doing with that with you, so handle that. And how do you proceed with such disclosures in the end? Yeah, so that were the experience from those disclosures. And what I also want to give to you, of course, are ways how to improve that for future disclosures, potentially that you are doing. So we handled also that in the project by providing much more information and to avoid such misunderstandings by sharing more information about the vulnerabilities, such as documenting every impact we saw with videos or photos to basically prove things that we saw even once, just to have the manufacturer to see what we really saw as an impact of the vulnerability and not only the vulnerability for itself. And also with the detailed description and somehow also recommendations for fixes, which is for easy problems also easier than for design problems, but that helped a lot also with manufacturers that were not that familiar with those processes. And of course, describing the disclosure process you're expecting is also a big deal, where you can avoid such misunderstandings in the means that you tell the manufacturer how responsive you are expecting him to be, of course, and also what the timeline should be for fixing such vulnerabilities by the prioritization he's potentially also giving to you. And also you should, of course, talk about the output in the end, because that may not only be fixing the vulnerabilities in the field. Yeah, I think it's completely clear that when such processes are not working that well, that you want to escalate it in some way, but of course, simply publishing those vulnerabilities is a no-go in that field. So you have to have some escalation path in that. And also what we saw is only that you can do that by communicating with the BfArM, which is the Federal Institute for Drugs and Medical Devices in Germany, which is basically a state-controlled office which is caring about those medical devices in the field. And also you could contact, of course, the BSI, or the Federal Office for Information Security, which in that means basically was performing that disclosures, but also that did not have a huge impact in the means that the manufacturers were behaving different, because the Federal Office for Information Security is not the same ministry as the Ministry of Health, for example, because the Federal Office for Information Security is the Ministry of Interior, so it's not covered by the regulation that basically the BSI was communicating with that manufacturer in the end. You have to include different persons from different institutes from that too. And what we did in the end was escalating that to a third. So that was the only means of ensuring the processes are getting further. So that's the point where we basically talked about the regulation and also about the case studies we saw. And we saw that many vulnerabilities in such devices are not really medical, specifically medical, but the operation environment and the impacts are, of course. And we also saw that the MDR, the regulation, is really nice in describing the current state and best practice of security validation testing and expectations you may have to security processes and functionalities that such devices have, or that the manufacturers are performing when developing that, and also, of course, after the device is being developed but being marketed, and that the post-market surveillance actions, of course, are a real big requirement that we should have had earlier in those means. But at the current moment, there are not that much devices certified after that new regulation, because that also takes some time with the new devices being developed, and there are also issues with that and challenges. So I think the requirements of the MDR are really nice, but we have to see how that really is evolving in the future to see the impacts of such harder requirements in the real world and in the wild. And also there are, of course, challenges for that. So that harder requirements will, of course, firstly impair updating the devices by changing them, because at the moment the manufacturer was allowed to proceed with the processes that the old law was describing until such a major change is being delivered. And of course, they now have to document and to change all their processes before fixing their devices, because otherwise they just would be audited after the new law, and their documentation and processes, of course, then need to be compliant to the new law. So that's a short-term impairment on that. And also, rendering those legacy devices compliant to the new law is a big issue. So that's mostly, I think, about the manufacturers and their devices, but from a perspective of that we are just having those devices in the field, and that there are the operators, of course, that are using them for their medical workflows. We also have to think about not putting on the switch just to have new devices now in there, and we're just putting out the old ones, but that we are, of course, replacing them one after another in a stepwise version. And then we, of course, have to care about the compatibility between those devices. So how do you operate an environment where you have insecure devices that also are being trusted by the new ones? So how do you handle such mixed environments in the end? And I think that's a huge challenge really for the manufacturers also to build the better devices in the end, but also for the operators, because they have to do decisions on that, how to handle that. And also, with the future, or let's call it state-of-the-art development processes and verification and technology, you will also see more modern technologies and features that the devices will support. So like, for example, what is the regulation telling about risks that may come from safety impacts that are here because your device has no cloud connection anymore by receiving updates or similar? Do you really want to have that? And also, what's the impact of then compromising that cloud deployment, for example, like services that are deployed there? So who's responsible for that? Do we need to audit the processes of AWS or similar for deploying medical software on those platforms? So I think there are still challenges to solve to, in the end, get in a phase where manufacturers and operators really have the large benefit of the new regulation in the end that really changes the medical devices we are using, and also changes the way of the problems that we are having, because I believe that we will not solve all of the problems with that one batch, but that the new regulation is putting everyone into position to actively tackle the problems we have, and to see the new problems that are potentially easier to fix and to handle, because we have the processes, and then can basically handle that with the shared responsibility of all of the entities that are or need to be considered, like the operators, the manufacturers, and also, of course, the patients that will use many of those devices. So that's the end of my presentation. Thank you very much for attending. Hope you got something new from that talk, and also learned the pitfalls and what the new regulation is doing. I really enjoyed it, and thank you very much.